Today we discuss on important topics partial derivatives. Okay, one of the important topics in calculus. In previous class we also discussed derivatives, directional derivatives and some examples. We also see directional derivatives. Directional derivatives give some value and derivatives also be a function, that means some operator. Okay, and then obviously here we also now proceed partial derivative. Here we write, let phi not equal to c subset of Rn with interior of c not equal to phi, and let e1 e2 e3 en be the standard basis of Rn, and then the partial derivatives of f, then the partial derivatives of f, then the partial derivative of f c2r at the point c, where c belongs to interior c, interior of c. Okay, at the point c, where with respect to x1 is del f by del x1. Okay, at point x equal to c equal to d1 if c, then this equal to d of e1 if c. Then directional derivative of f, this equal to directional derivative of f at c along e1. Okay, equal to limit t tending to 0 f of c plus t e1 difference of f of c divided by t. Now del f by del xi, that means partial derivative with respect to xi at x equal to c equal to limit t tending to 0. Here f of c plus tei difference f of c divided by t. Okay, then this one is called partial derivative with respect to, that means directional derivative in a particular direction. Okay, now we also write some example. We'll erase this portion and going to some example of partial derivative. We write here if xy equal to, example, if xy equal to xy divided by x square plus y square, and here xy not equal to 0 0 and here xy equal to 0 0, then what happened? Then del f by del x equal to here y by this one, sorry, this one whole square, this one whole square multiplied by, not if, del f by del x, not this way, del f by del x at what point is this one is affected? Here 0 0 point equal to how much? Equal to here we construct del f, that means d of d of d of dx of 0 0, that means here 1 0 in this direction. So here if we write, then this one is limit t tending to 0 0 f of 0 0 plus t into 1 0 difference f of 0 0 y t equal to limit t tending to 0, here f of t0 difference f of 0 0 y t, then this one equal to 0. Okay, and in this similar way del f by del y 0 0 at 0 0 point equal to 0. Here we write t into 0 1. Then but here we also see that d of xy f of 0 0 does not exist. Okay, because here f of t and then this one t square by t square, here 1 by t is right exist, then this one is does not exist. Okay, so we also give some example which have partial derivative at 0 0 exist but directional derivative does not exist. Okay, then we're going to remark of this. From above example, we can say that the partial derivative of a function which is not continuous may exist, but directional derivative may not exist. Okay, then we erase this problem and obviously discuss some directional derivatives of a vector valued function. Okay, we erase this example also and going to further discussion about that. We also write directional derivatives of a vector valued function, Okay, then what happen here? We write let phi not equal to c subset of Rn with interior of c not equal to phi, with interior of c not equal to phi, and let if c to Rn be a function, c to r to the power n be a function defined by fx equal to f1x f2x dot 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 fn x. Okay, where x belongs to C and where fi x equal to where fi x C to R are called called the components of F. Called the components of F. Are called the components of F. Then the directional derivative of F at point C is in the direction u belongs to Rn is denoted and defined by. Then the directional derivative of f at point C in the direction u belongs to Rn is denoted and defined by DUFC equal to limit t tending to 0 f of c plus tu difference f of c divided by t equal to f dash c u equal to du f1c du f2c dot 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 du fmc. Then we obviously discuss that portion. Okay, this one is the directional derivatives of a vector valued function. Okay, then also discuss we know about that some directional derivative of a scalar function, and here obviously directional derivative of a vector valued function. Okay, now partial derivative of vector valued function we also discuss. We erase that portion now. Partial derivative of vector valued functions. Okay, what we write here, the partial derivative of f at point C, the partial derivative of f at point C with respect to xi is denoted and defined by with respect to xi is denoted and defined by is denoted and defined by del f by del xi c equal to difc equal to limit t tending to 0 f of c plus tei difference f of c by t equal to d of f1 del xi c d of f2 by del xi dot d of fn c by del xi. Okay, for all I equal to 1 1 m. Okay, or I equal to 1 1 n, because here 1 to n. Then we also discuss this one, partial derivative of vector valued function. That means del f by del xic equal to difc equal to limit t tending to 0 f of c plus tei difference fc by t equal to del f1 by del xic del f2 c by del xi del fmc by del xi for all I equal to 1 1 n. Okay, then we also going to Jacobian of a function. We will erase this portion and going to another discussion about that Jacobian of a function. Okay, now we are also going to Jacobian of a function. So we write here Jacobian of f. Jacobian of f. Okay, then let phi not equal to c subset of Rn with interior of c not equal to phi with interior of c not equal to phi. Let f c to Rm be a function. Let f c to Rm be a function defined by f of x equal to f1x fmx such that all partial derivatives of f exist. All partial derivatives of f exist. Okay, then the Jacobian of f, then the Jacobian of f at point C is denoted and defined by JFC equal to del F1C by del X1 del F1C y del x2 dot 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 del f1c y del xn del f2c y del x1 del f2c y del x2 dot 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 del f2c y del xn. Here del fmc y del x1 del fmc y del x2 dot 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 del fmcy del xn. Okay, so this one is the Jacobian of f at point c. Okay, so next we also discuss some Jacobian of these functions. That means we also create some function and going to Jacobian of this. We see the Jacobian how much is determined. Okay, then we erase this portion now. Find the Jacobian of the function. Find the Jacobian of f r squared to r cube by f of xy equal to x y x plus y at point AB. Okay, at point AB is what JF AB equal to, we do here del f1 AB by del x1. Okay, next del f1 AB by del x1. Okay, next del f2 AB by del x2 and del f2 AB by del x2. Here del f3 AB by del x3 and del f3 AB by del x3 equal to how much? Okay, equal to what we get from here. This one equal to 1. Here obviously we get again here del f1 by del x1. Sorry, this one is x2. Of this one x1, this one x1, this one x2. Okay, then this one 1, this one equal to 0, and here del f2y, then this one 0, this one 1, and del f3 equal to this one 1, this one 1. Okay, here we going to this Jacobian equal to 1 0, 0, 1 and 1, 1. Okay. Now we also erase this portion and obviously find Jacobian of others function. Okay, we erase that portion and obviously this one also AB point. Then then here we write what? Here we write f of x y. F of x y equal to x square y square, x square plus y square. Here x cube y square. Here x square y cube. Okay, at point AB. Then JF AV equal to del F1 AVY del X1 and del F1 AVY del X2 and del F2 AVY del X1 del F2 AVY del X2 del F3 AVY del X1 del F3 AVY del X2 equal to what? Here we write equal to 2x, x means a. Here obviously 2y, that means b. F2 3 a square y square, that means 3 a square b square. Here 2 a cube b. Okay, then next obviously 2 a v cube. Here 3 a square v square. Okay, in this way we also find Jacobian of this function. Again we also see another function's Jacobian we also see now. So we erase this portion and going to be discussion of another function's Jacobian. Okay, oh sorry, these functions obviously r cube to r cube. Okay, this function, sorry, r squared to r cube, this one is okay. Okay, I'm not r squared to r cube, this function is okay. Now we discuss another function which are going to r squared to r cube. Okay, then what happened now? We also discuss find now this function is r cube to r cube and obviously if xyz equal to x square plus y square, here x square minus y square, here x cube y cube z cube. Okay, at point obviously here ABC. Then what we find here JF of ABC equal to, we write direct here 2a 2b and 0, here 2a, here minus 2b and 0, here 3a square b cube c cube. Here 3a cube b square c cube. Here 3a cube b cube c square. Okay. Then we're also going to another problem. We find Jacobian of this. Here we write f of xyz equal to x square y square z square and z square x square. That means f is defined from r cube to r. Okay. Then what happened if we find jf of abc? Jf of abc equal to this one, just one function. So we write here 2a b square. Here not possible. Here 2a c square. This one comma. Then again in respect to y, here 2a square b and here 2 c square b. Again then 2 b square c plus 2 a square c. Okay. Then we also find this Jacobian. So today we discuss about Jacobian of a function and partial derivative of vector valued function and directional derivative of vector valued functions and definition of partial derivatives. Okay, these portions today we discuss. So now we discuss in next class. Now stop here.